So we can alter the rate of a chemical reaction by changing the concentration of the reactants, or we can change the temperature in which the reaction is occurring. But there are limits to how much those can have an effect. You know, you can't heat up an aqueous reaction past the boiling point, so you can only get it so hot, right? You can only increase a concentration so much before you encounter the solubility limit. Well, there are other ways to increase the rate of reaction. One of those is a catalyst. So a catalyst increases the rate of reaction but is not used up. It does not get consumed. And how this works is it provides a different mechanism. It provides an alternate mechanism in which the rate limiting step has a lower activation energy. Lower activation energy, faster reaction. So, looking at the decomposition of ozone, the uncatalyzed reaction happens in a single elementary step. An ozone molecule collides with an oxygen atom and makes two oxygen molecules. So we have a transition state here, and there's an activation energy. Because that activation energy is high, the rate of that reaction is very slow, or fairly slow. And so the ozone layer does not just rapidly decompose into oxygen. It hangs around. But if chlorine atoms are present, they can act as a catalyst by making another pathway that has a lower activation energy. So if the catalyst makes possible a different way to get through this that requires less energy. And so then the reaction will proceed at a faster rate. So the mechanism for catalytic destruction of ozone is that a chlorine atom interacts with an ozone atom and forms chlorine monoxide and oxygen gas. And then this chlorine monoxide reacts with an oxygen atom and returns the chlorine atom that we started with and forms an O2. So the rate limiting step here has a lower activation energy, and so the reaction is going to occur faster. The chlorine does not get consumed. It's involved in the reaction, but it doesn't get used up. So here the chlorine becomes part of this intermediate, but when the intermediate reacts, the chlorine is reformed by itself. And so it's available to catalyze another reaction. When we add these steps together, we get the same overall reaction. Well, where do the chlorine atoms come from that catalyze the destruction of ozone? They come from us, our activities. Chlorofluorocarbons. These have been used historically in, Freon, which is in your air conditioner, also as propellants in aerosol cans. And so they're hydrocarbons that have chlorine and fluorine atoms on them. And when these get into the atmosphere, the light from the sun can cause them to decompose, releasing chlorine and fluorine atoms. And the chlorine atoms then can catalyze the destruction of ozone. Another example of catalysts is a catalytic converter. So catalytic converter has a solid catalyst. In the destruction of ozone, we were looking at a gas catalyst, chlorine gas. Well, atomic chlorine. In the catalytic converter, you've got something like platinum, rhodium, or palladium that is on a high surface area substrate. And this is the reason that people go around stealing catalytic converters, is because they have platinum and palladium and rhodium in them, which are expensive metals. And so they can sell them and get some money for them. So what happens in the catalytic converter is that you have the combustion products from the gasoline coming through here, and we're going to take NO and CO, nitrogen monoxide and carbon monoxide, which are somewhat harmful, and we can convert them into less harmful substances, nitrogen gas and carbon dioxide gas. And you may say, well, carbon dioxide, we don't want that. Well, no, we don't want too much carbon dioxide, but we do need carbon dioxide in the atmosphere. And carbon dioxide is much less harmful than carbon monoxide. So the exhaust pollutants are converted to less harmful substances, and it also promotes the complete combustion of fuel fragments. So, ideally, all of the hydrocarbons in your fuel would combust completely into carbon dioxide and water, but nothing ever works that well, right? So you may end up with some fuel fragments, and these aren't good to be spewing out into the atmosphere either. And so these will also get more completely reacted. And so as the product's out, if everything's working really nicely, we're going to get nitrogen and carbon dioxide and water. Pretty harmless things. Any questions? So this is an example of a chemical reaction occurring in the gas state, but being catalyzed by a solid. So homogeneous catalysis is like the catalytic destruction of ozone, where the catalyst and the reactants are in the same physical state, the same phase. They're both in the gas phase, they're both in the liquid phase. So in the destruction of ozone, everything's in the gas state. Heterogeneous catalysis is where the catalyst is in a different state phase than the reactants. An example of that is a catalytic converter. So heterogeneous catalysis, we have our reactant molecules here and our products in the gas state, but the catalyst is a solid, different state. Here, all of it's in the same state. Okay? So you may be aware that there is an ozone hole that develops over Antarctica. What's really interesting about this is that it is not always present. So we talked about chlorine as being a factor in the destruction of ozone, but chlorine is evenly distributed throughout the whole atmosphere. So why would we see a huge drop in the ozone in this one area due to chlorine? It can't be the chlorine. Well, what happens is that the chlorine from those chlorofluorocarbons gets bound up in other substances, such as ClO and O2, that prevent it from catalyzing ozone destruction. Those chlorine atoms are not very happy on their own. They would like to be part of a molecule, and so they're going to react with other things. They'll react with ozone, but they'll also react with other things, and so they'll get bound up in other things. So that's why we haven't completely destroyed all the ozone. So clouds over the South Pole, polar stratospheric clouds, have ice particles in them. So, we think of clouds as being droplets of water. Well, if it's very cold, they're droplets of ice. And those ice particles catalyze reactions that release chlorine. In the Arctic Spring, which is, the opposite of our spring, the sunlight is stronger down there. It's like the sun never sets during the Arctic spring. The sunlight can catalyze the dissociation of chlorine molecules into chlorine atoms. And now we have these chlorine atoms present in a much higher concentration than in the rest of the atmosphere because of these clouds catalyzing the release of chlorine. So what happens then is we get an ozone hole that forms every spring, and it lasts for about 6 to 8 weeks, and then this catalyzing from the clouds settles down, and we don't have as much chlorine, and then the ozone comes back. And so, you can look at one piece of data and say, oh, there's this huge hole, this is terrible. But then later, it's gone, right? So it's definitely a concern, and, there's legislation and everything that we don't use chlorofluorocarbons very much at all anymore because it was found to destroy ozone. Anybody have any questions about that? Another example of catalysis. So the reaction between ethene, which is a 2-carbon hydrocarbon that has a double bond, the reaction between this and hydrogen is pretty slow at normal temperatures. But if we have a catalyst of finely divided platinum, palladium, or nickel, then the reaction occurs rapidly. So the large activation energy for that reaction is due to the strong hydrogen-hydrogen bond. When these reactants adsorb onto the catalyst surface, that hydrogen-hydrogen bond is weakened, and the reaction can occur much faster. So here we have an illustration of 4 steps of heterogeneous catalysis. The first is absorption, adsorption, not absorption. So adsorption, the reactants are adsorbed onto the metal surface. So we've got gases sticking to this metal surface. And then we have diffusion. So the reactants are going to move around on this surface until they approach each other. The reaction occurs, the reactants react to form products, and then the products desorb from the surface. They leave the surface. Enzymes are very, very important biological catalysts because most of the reactions that are needed for an organism to survive are too slow to support life under normal conditions. So enzymes are biological catalysts. These are usually large protein molecules. The reactant molecule is called the substrate, and it will bind to an active site of the enzyme, and it does so through intermolecular forces like hydrogen bonding. When that reactant molecule is bonded to this active site of the enzyme, then the activation energy of the reaction is lowered and the reaction occurs much more quickly. So here we have the general mechanism. So an enzyme plus the substrate. So this is fast, forming this enzyme substrate complex. So the substrate fits in. They often talk about a lock and key analogy. So this is like a key fitting into the lock. Only certain substrates can fit into here. So these are selective catalysts. So this comes in here. And in the process of being stuck into that active site, then some of these bonds are strained, and that makes it easier for the reaction to occur. But this enzyme substrate complex going back to the enzyme and the products, that's the slow or rate limiting step. So let's look at this for sugar. Sugar has a high activation energy for its hydrolysis. Hydrolysis of sugar, of sucrose. Sucrose is a disaccharide. It's got two sugars bonded together. So there's a glucose part and a fructose part. And to metabolize sucrose, you need to break these apart, and then you get glucose and fructose. Well, the bond that needs to be broken is right in here. And the reaction rate for hydrolyzing sucrose at body temperature is slow. It's not going to happen very fast at all. But when the sucrose is in the active site of the sucrase enzyme, it causes a strain on this bond and weakens it. So as the sucrose comes into this active site, it has to kind of get tweaked. It gets stretched a little bit, and it weakens that one bond that's going to be broken. That lowers the activation energy, and so the sucrose can be hydrolyzed more quickly. That make sense? The point of all of this is not to discuss in great detail catalysts or enzymes, but to help you understand the big idea chemically for how they work. You know, you're taking biology or biochemistry or something, they'll go into the details of the enzymes, right? But this is the idea of how they work. It's lowering the activation energy so that the reaction can occur faster. Once this sucrose molecule is hydrolyzed, the pieces leave because it's no longer just the right shape, and so they're going to come off. And the sucrase enzyme is ready for another one. So the catalyst does not get used up. So enzymes give organisms amazing control over which reactions occur and when they occur. So your body can turn enzymes on, it can form enzymes, release enzymes in order to make specific chemical reactions occur as needed. And those enzymes are very, very specific. They each catalyze just a single reaction. And they have a tremendous effect. They can speed up a reaction rate by as much as 1 billion times. I mean, just mind-boggling, really. So some of the very, very toxic substances are so very toxic because they inhibit enzymes. So if you have a substance that interferes with the active site for the hydrolysis of sucrose in sucrase, it gets stuck in the active site and the enzyme can no longer catalyze the hydrolysis of sucrose. You can't metabolize sucrose anymore. And just getting rid of one enzyme could prevent the reaction of billions of sucrose molecules. And so, things that do that can be very, very toxic. Any questions? That's the end.